PU2 warriors, welcome to Deeksha Karnataka YouTube channel and in your favorite Brahmastra series. Today I am going to discuss a very important chapter, electrostatic potential and capacitance. So before I start with this lecture, I just want to share the new blueprint from this chapter. So basically here they have mentioned 1 mark question. One of the questions will come from this chapter, and one question will come as short answer type, 2 marker, short answer type 3 marker will be there as 1 question, and long answer type 1 question. Now as you know that in the blueprint they have not mentioned whether this 1 marker will be for MCQ or this will be for your fill in the blanks. Also the clarity of this long answer type, whether it will be a theory based question or a numerical based question, we have no such clarity. Okay, but we know that this chapter is important for MCQs, but we will also practice some fill in the blanks in for reference, and long answer type questions will be practiced, both theoretical questions as well as numerical, because this chapter and electrostatic field chapter, they are like coming in a pair. So if theory question comes from the first chapter, numerical question comes from the second chapter, and vice versa. So how many questions we are going to discuss in this session? So we are going to discuss 15 MCQs as usual. We will also discuss 5 fill in the blanks. We will discuss 5 2 marker question, 4 3 marker question, 3 long answer type questions, and also we will be discussing 4 numerical questions as well. So without much delay, let us start with the MCQs first. 2 capacitors of capacitance C1 and C2, C1 not equals to C2, are connected in parallel to an external source of potential difference V. The equation which is not applicable for the given combination is. Symbols have their usual meaning, so let us understand what is the question is talking about. So here we have 2 capacitors C1 and C2. They are connected in parallel with the voltage source V. Okay, so this is how the connection goes. This is C1, this is C2, and this is V. Okay, now they are asking you that the equation which is not applicable. Not applicable means out of these 4 equations, 3 are applicable, so 3 are correct, only 1 is incorrect. That incorrect one you have to identify and answer. Okay, so first of all, if charge stored over here is Q1, here it is Q2, then the total charge in the circuit, whatever is stored, Q is equals to Q1 plus Q2. Okay, so definitely this is a correct statement. Now what about V is equal to V1 plus V2? So we know that in parallel combination, if voltage you apply is V, then the same voltage is applied across this, and same voltage is applied across the second capacitor as well. So V equals to V1 plus V2 is not correct. So this is our answer. This one is our answer, but we will check the other 2 options as well. C equals to C1 plus C2. So equivalent capacitance in parallel combination is given by C1 plus C2. So this is a correct statement. And as I mentioned, V1 is equals to V2. We know that in parallel combination the voltage remains same. In fact, this is equals to the voltage of the battery. So this is also a correct statement. So only incorrect statement is option B. Now let's move on to the question number 2. The electric potential at a point due to a point charge varies with the distance from it as 1 upon r, 1 upon r square, 1 upon r cube, 1 upon r to the power of root r. So electric potential at a point due to a point charge. So electric potential due to a point charge is given by V is equal to KQ upon r, not r square, not r cube, but only 1 upon r. So correct answer is option A. Okay, this question I have taken it from your blueprint. In the blueprint, instead of r they have mentioned distance. So instead of distance I have taken it as r. Okay, that is the only change I have done myself. Otherwise the question is same. Next, before I continue, I just would like to remind you that join our WhatsApp channel. The link of the WhatsApp channel is given in the description. Also, please don't forget to subscribe to our channel. Subscription is very, very important for our channel to grow. Now, by the time I am recording this lecture, we have already crossed 1 lakh, but anyway, we want more of your support. So please do share this video with your friends, your classmates, so that this channel can grow very fast, right? Our target is not yet achieved, so please share this video with as much as possible. Also, ask them to join our WhatsApp channel as well. Link of the WhatsApp channel is given in the description of this video. Now, question number 3. The capacitance of a capacitor is 6 times 10 to the power of minus 6 farad. It is connected to a 200 volt cell. The energy released on discharging it fully will be. So how much energy is released when you discharge a capacitor? Capacitance is given by 6 into 10 to the power of minus 6 farad, and it is connected to a 200 volt battery. Right? Now, first of all, you have to understand that when you are discharging a capacitor, that means first of all you have to charge it. So when you charge the capacitor, how much energy it can hold? So that much energy will be released when you are discharging it. So how much energy can be stored in a capacitor is given by half CV square, because voltage is given, capacitance is given, so we will use this formula to calculate how much energy it can store. So half into capacitance is 6 into 10 to the power of minus 6 into 200 whole square. Now this question came in 2024 exam. Okay, so this is the PYQ. 3 into 10 to the power of minus 6 into 200 into 200. So how many zeros are there? 1, 2, 3, 4. 4 zeros are there, and 10 to the power of minus 6 is there. So we can write 3 into 4 into 10 to the power of minus 2. Okay, 4 zeros are reduced from this minus 6. Now we have 3 4s are 12 into 10 to the power of minus 2. So that is 0.12 joules. So the energy that is released here is 0.12 joules. Option A is correct answer. So this is a short, very short numerical came in your previous year question. Now, if n identical capacitors of capacitance C is connected in series, then the equivalent capacitance is. So here we have n capacitor, each of them have capacitance C, and you are connecting them in series. So what is the equivalent capacitance? We know that in series combination they add reciprocally, so equivalent capacitance in this case will be C by N. If it is connected in parallel, then the capacitance will be N into C. So correct answer is option C, C by N. Now let's move on to the next question. If charge in a capacitor is doubled, then the capacitance is. So we know that Q equals to CV. So you might think that if I double the charge, capacitance should be doubled. Actually no, capacitance is given by Q upon V, and if you increase Q, the voltage will increase, but the ratio of charge and voltage will remain constant. Capacitance is actually a proportionality constant, and that's why it is a constant no matter if you change charge, if you increase voltage, the capacitance will remain same. To change capacitance, what you have to do? You have to go to its dimension, that is you have to change the distance between the plates, you have to increase its area, or you can add a dielectric medium between the plates. That's how you can change the capacitance, right? So the formula for changing the capacitance is K epsilon naught A by D. So if you change any one of them, the capacitance will change, but by changing charge or voltage, capacitance will not change. So correct answer is remain same, option C. Question number 6. At the surface of a charged conductor, electrostatic field must be. So at the surface of a charged conductor, we have a charged conductor. And what about the electrostatic field? So they are asking about electrostatic field, not electrostatic potential. So it will be either it will be 0, parallel to the surface at every point, infinity, normal to the surface at every point. We know that from the property of conductors that electric field on the surface of the conductor is not 0, but it is normal to the surface. So it is normal to the surface at every point. This is the correct answer, not 0. 0 is inside the conductor, electric field is 0, but on the surface it is not not 0, and neither it is infinite. Okay, next question. The electric field inside the cavity of a charged conductor is 0. This is known as electrostatic shielding. So inside a charged conductor, if you have a cavity, cavity means the cavity that you might have in your teeth, okay, a gap, okay, a hollow space. So cavity means metal is there, okay, outside, but there is no metal inside. This is called a cavity. Okay, cavity means a hollow space where nothing is there. Now if you measure the electric field inside this cavity will be always 0, and that is called electrostatic shielding. Next question. Dash dielectric develops a net dipole moment in the presence of an external field. So which type of dielectric develops dipole moment in the presence of electric field? Presence of external electric field, both polar and non-polar develops dielectric moment. In case of polar, they already have a net dipole moment in molecular level, but in the material level, net dipole moment cancels each other, so net dipole moment will still be 0. But when you apply external electric field, not only the polar ones but non-polar ones both get electrically polarized. So both polar and non-polar will be the answer. Clear? Right? Both polar and non-polar dielectric develops net dipole moment in the presence of external electric field. Next question. What is the total charge on the parallel plate capacitor? So here they have given you a diagram and they asked you what is the total charge on the parallel plate capacitor. So in this case you can see that total charge of a capacitor is given by Q plus minus Q, that is equals to 0. Okay, charge of a capacitor is Q, but total charge always will be 0. Total charge in a capacitor will always be 0, but when we say the charge of a capacitor, we generally take the positive value. So total charge will be 0. Correct answer is option D. Next question. Potential due to a charge Q at its own location is. Potential due to a charge Q at its own location is 0, infinite, between 0 and infinity, minimum. So let's see. So potential due to a point charge is given by KQ by R. Now at its own location, when the charge itself is located, okay, at its own location R equals to 0. Okay, at the location of the charge, the distance is 0. So if you put distance 0, then you get KQ upon 0, which is equals to definitely infinity. So at its own location, not only potential but electric field is also infinity. Due to a point charge, whenever you are considering a point charge, at the location of its at its location, the field and potential both becomes infinity. The capacitance of an air capacitor is C0. A dielectric medium of dielectric constant K is inserted between the plates. Then the new capacitance will be. So air capacitor, the capacitance is given by A epsilon naught by D. Now when you add a dielectric medium, the same capacitance becomes A epsilon naught by D, so it basically K times C0. So capacitance becomes K times, that's why we use dielectric medium. So correct answer is KC0, option D. Next question. The electric potential at the surface of a conducting charged spherical shell of radius 10 centimeter is 20 volt. The electric potential at the center of the shell is. So we have electric potential on the surface is given by 20 volt on the surface. So if the potential at the surface is 20 volt, then inside the shell will also be 20 volt. It will be constant. Okay, potential is constant inside a shell, inside a conductor. Electric field is 0, but potential is constant. So the answer will be 20 volt. Okay, next question. The values of electric field E and electric potential V at any point on the equatorial plane of an electric dipole are such that. So on the equatorial plane of a dipole, what is the electric field, what is the potential? So on the equatorial plane, electric potential you already know, it is given by E equals to equatorial plane equals to minus 1 by 4 pi epsilon naught P by R cube. Okay, so this is the equatorial plane, potential on the equatorial plane. Now what about electric potential? So electric potential normally at any position is given by 1 by 4 pi epsilon naught P cos theta by r square. This is the general expression, right? Now for equatorial plane, what is the angle theta? For equatorial plane, the angle theta is obviously 90 degrees. So what is the electric potential? So electric potential on the equatorial plane is definitely equals to 0. Okay, so that is a small mistake. This is potential we are talking about. So the symbol has to be that of potential. So this will be V. Okay, so V equipotential at the equatorial plane must be 0, and also it can be proven from the fact that one is positive charge, another one is negative charge, so net potential will cancel each other because distance is same, so it will be 0. So electric field is not 0 but potential is 0. So option C is correct. Electric field is not 0, potential is 0, so option C is correct. Next question. The angle between equipotential surface and the dielectric field is. So angle between equipotential surface and the electric field is, so if there is a equipotential surface, then the angle between equipotential surface and electric field is always 90 degrees. So correct answer is option A. Next question. A spherical conductor of radius capital R is carrying a charge of capital Q. The ratio of the electric potential corresponding to a point on the surface of the conductor and a point at a distance 2r from the center of the conductor are in the ratio. So let's see. Electric potential, the charge that is being carried is plus Q. The radius is given by r, and what will be the potential at 2r? We know that on the surface of a conductor or inside the conductor, electrostatic potential is constant, and that is given by k q upon r. What about at a distance 2r? It is given by v dash equals to k q by 2r. As simple as that, only 1 upon r. So v by v dash equals to kq upon r divided by kq upon 2r. So it will be 2, and the ratio will be 2:1. Ratio will be 2:1, not 1:2. Order, whenever there is a ratio based question, make sure what is the order. So electric potential corresponding to a point on the surface first, and second is at a distance 2r. So on the surface first and the second point is next. So that's how you calculate the potential ratio. So ratio based question, the order is very important, because you can see 2:1 is there, 1:2 is there. So if you have calculated v dash by v, you might have thought that okay, maybe it is 1:2. So whenever you are solving a ratio based question, make sure that you are correctly calculating the ratio order. Now let's move on to the fill in the blanks. A molecule possessing permanent dipole moment is called dash molecule. So a molecule which possesses a permanent dipole moment is called polar. Let's see if it is given in the option or not. Yes, polar is given, so definitely the correct answer will be polar molecules. Next, the potential due to a dipole depends on dash. So potential due to a dipole can be depends on many things. Let's see the options. Non-conducting, not making any sense. Nanofarad, not making any sense. Distance could be an answer. Let's see. Increases, decreases. So potential due to a dipole depends on increases, decreases. Also not making any sense language wise. So that means the correct answer for this will be distance. So we know that electric potential and electric field both depends on distance. So correct answer is distance. So for example, electric potential due to a dipole also depends on the dipole moment, but dipole moment is not given in the option. So make sure that whatever is the correct answer, you make sure that this is making sense and the sentence is complete. As the distance between the plates of a capacitor is increased, the capacitance. So distance between the plates is increased. So what will happen to the capacitance? Whether it will increase or it will decrease. So increases and decreases both are given. So one of them will be answer for this question. Let's see. Capacitance is given by normal air capacitor A epsilon naught by D. So capacitance is inversely proportional to the distance. So if distance is increasing, then capacitance must decrease. So if the distance between the plates of the capacitor is increased, then capacitance must decreases. Capacitance is measured in, so what is the unit of capacitance? So out of all these things, the unit of capacitance is given by nanofarad. So nanofarad is the unit of capacitance. Correct answer will be nanofarad. Dielectrics are dash substances. So dielectrics are actually non-conducting substances. Okay, so dielectrics are non-conducting substances. Now let's move on to the 2 marker section. So now we will be discussing few 2 marker important questions. What is an equipotential surface? What will be the shape of equipotential surface corresponding to a single point charge? So any surface which has the same electric potential at every point is called an equipotential surface. The shape of equipotential surface is spherical for a single point charge, and you also have to draw a diagram. Okay, this is the 2-dimensional representation of a 3-dimensional thing. A spherical equipotential surface becomes circle in 2 dimensions. That's how you can represent it. Next, what factor does the capacitance of a parallel plate capacitor depends? So factors, we know that capacitance is given by Ka epsilon naught by D. Out of that, epsilon naught is an universal constant, so it depends on dielectric, it depends on area, it inversely depends on the distance between the plates. So if you are mentioning over here, you have to mention that capacitance is directly proportional to area, capacitance is directly proportional to the dielectric, and 3 you can mention capacitance is inversely proportional to distance. Okay, if you write it in terms of word, that is fine. If you are writing in terms of variables, then this equation is must. Okay, then this equation is must, and you have to mention what are all these variables means. Okay, I will tell you that you should write them in terms of words. Okay, capacitance is directly proportional to area, capacitance is directly proportional to the dielectric medium between the plates, capacitance is inversely proportional to the distance between the plates. Now whatever you are comfortable with, you can write, but if you write only like this, teacher may be unhappy. Next, write 2 properties of equipotential surface. Now this question can be as a 3 marker question as well. So in 3 marker you have to write 3 properties, in 2 markers you have to write 2 properties. No work is done in moving a test charge over an equipotential surface. So work done to move a test charge in an equipotential surface is 0. Electric field is always normal to the equipotential surface at every point. No 2 equipotential surfaces can intersect each other. This is similar to the electric field. No 2 electric field lines can intersect each other. Similarly, equipotential surfaces can also not intersect each other. The electrostatic potential energy of a system of 2 like charges is positive. Explain. So this question is from one of your model paper this year, latest model paper. So let's see. So electrostatic potential between 2 point charges is given by Q1 Q2 by R. So we have 2 charges, Q1 Q2 and R. Okay, so if 2 charges separated by a distance R, then that is their equipotential surface. But if you just write this equation, you will not get any marks. Okay, you have to explain why it is positive. When 2 charges have the same sign, both can be positive or both can be negative. They repel each other. So normally when both charges are of same sign, they repel each other. Like charges repel each other. Okay, due to electrostatic force. To bring these charges closer together, so if I want to make the distance smaller, okay, then what we have to do, you must do work against this repulsive force. Okay, so when charges are repelling each other, they are trying to move away. But what you are trying to do, you are trying to bring them closer. That's why, that means you are trying to apply some force, and you have to apply the force externally. So external force has to be applied to bring them close. And we know that if external force is to be applied, then that work we consider positive. Okay, so work done, this repulsive force, the closer you try to push them, the stronger they repel and more external work you have to do. So that's why the potential energy of a system of charge, potential energy of 2 similar charge is positive. Okay, Now next question, what is meant by equipotential surface? Same question. Okay, draw the equipotential surface for an electric dipole. So this is a new question again from your new model blueprint. Previously the question used to come for a point charge. They have added dipole this year. So almost similar, only thing you have to be careful, equipotential surface is the surface which has the electric potential remains same at every point. So definition is same, but when you are drawing the dipole, make sure that these lines are little closer. These lines are slightly wider. Again, these lines should be slightly closer. This line should be slightly wider. Okay, the gap should be like that. Okay, so how to do that? Positive, negative, and what you can do, you can draw them like that. Okay, you don't need to use a compass. Okay, you can use your hand so that it appears that it is like this. Okay. So make sure dipole, electric field lines of a dipole and equipotential surface of a dipole are separate. So make sure you are doing the correct diagram. Next, obtain the expression for effective capacitance of two capacitors connected in series. So either series or parallel, any one of them can come as a 3-marker question. So first we will start with series. So here we have two capacitors. They are asking you only two capacitors, so no need to add more. Two capacitors is sufficient. So two capacitors, C1 and C2, they are connected in series. They have a battery. This is C1, this is C2. Now what? Now you have to be careful what is happening in case of series combination. In series combination, we know that the current in the circuit remains same. In case of capacitors, instead of talking in terms of current, we talk in terms of charge. So total charge in the circuit remains same. So whatever charge is stored in the capacitor C1, the same charge must be stored in the capacitor C2. So both capacitors should have the same charge, right? Now what? So we will start with the concept of equivalent circuit. Concept of equivalent circuit is when you replace the combination of capacitors using a single capacitor such that everything remains same. That means the charge in the capacitors remains same. Okay, you applied the same voltage. So this is called equivalent circuit. Okay, now first we will see what is happening in each and every capacitor. Suppose the voltage drop across this is V1, voltage drop across this is V2. Okay, we know that Q is equals to CV1 or C1 V1, or V1 equals to Q by C1. This is for the first capacitor. Similarly, for second capacitor, we can write V2 equals to Q upon C2. Now what? So this is the voltage across these two capacitors, and you have applied only one external source, that is V. So that means V must be equals to V1 plus V2. Okay, now put the values. V equals to Q upon C1 plus Q upon C2, or Q common, you get 1 upon C1 plus 1 upon C2. This part is done. Now we will do the same mathematics for equivalent circuit as well. Now if you do the same mathematics for equivalent circuit, what you get? Charge stored is Q, C equivalent is capacitance, voltage you applied is V. So Q again is equals to C equivalent into V, or V equals to Q upon C equivalent. So from this equation we will put that over here, and we get Q by C equivalent is equal to Q common 1 upon C1 plus 1 upon C2. So Q gets cancelled, and you get 1 upon C equivalent is equals to 1 upon C1 plus 1 upon C2. This is the expression for capacitance of two series combination of capacitors. Okay, now let's move on. Obtain the expression for effective capacitance of two capacitors connected in parallel. Now same question, only thing is we are using it for parallel combination. And what is common in parallel combination? What remains same in parallel combination? In parallel combination, the thing that remains same is voltage. Charges vary. So this is Q1, this is Q2, this is say C1, this is say C2, and the voltage that you have applied is V, and the equivalent circuit is everything remains same. The total charge remains same, that is Q, and this is V, this is the C equivalent. Okay, this is the equivalent circuit. Okay, in parallel combination the voltage remains same across both capacitors. So from there we can say Q1 equals to C1 V1 and Q2 is equals to C2 V2, or because the voltages are same, let me just write them as C1V and C2V. Now what is the total charge Q? By the way, total charge Q must be equals to Q1 plus Q2, right? Total charge must be Q1 plus Q2. So that means again for the this circuit we can write that Q must be equals to C equivalent into V. Okay, this is for equivalent circuit. Now we will put that Q over here and these Q's over here. We get C equivalent into V equals to C1V plus C2V. V gets common, C equivalent equals to C1 plus C2. It gets common and gets cancelled as well. So we get C equivalent equals to C1 plus C2. So this is the easiest of the two. Okay, series one is more common in exams because it is slightly tricky. Parallel one is easier, that's why they generally do not ask parallel combination. Now give three results of electrostatics of conductors. Now this question was there in your last year's blueprint and it is still there in your this year's blueprint as well. So this question, even though this question never came, this might come in your board exam. Inside a conductor, electrostatic field is 0. At the surface of a charged conductor, electrostatic field must be normal to the surface at every point. The interior of a conductor can have no excess charge in the static situation. So these are the three properties, three results. Okay, also you can add that if there is a cavity inside a conductor, electric field is 0 inside a cavity. That is called electrostatic shielding. Now derive the relationship between electric field and electric potential due to a point charge. This is one of the VVIP question. Okay, almost every alternate year this question comes. For that, first of all you have to draw this circuit diagram. So you have to draw this diagram first. So this diagram is basically representing the potential at some point V and at some point A and at some point B. Okay, so these are the two equipotentials. We call them equipotentials. So and we have a test charge which is kept at point A. We have a test charge kept at point A and we are trying to bring this test charge at point B or point P. Okay, I don't think it is P, let me maintain B only. So here we are trying to bring this test charge from A to B and we will try to calculate what is the work done to bring it. Okay, there is a relationship between work done and potential. So that theory we will try to explore. So what is the initial potential energy of this test charge? Initial potential energy is given by UI equals to Q into V. Initial potential energy, and as you are moving from higher potential to lower potential, final potential energy is given by Q into V minus delta V. Right, this is the change in potential energy. Now what is the work done? Work done is given by change in potential energy, that is equals to UF minus UI. Remember, always final minus initial. Be it positive, be it negative, does not matter. So Q into V minus delta V plus Q V. So if you can calculate it, you will get minus Q into delta V. Okay, minus Q into delta V is the work done to move a positive test charge from point A to point B. Now this is one thing. Now we will use our mechanical formula to calculate work done. Okay, so these two points A and B are very close. Okay, why I am saying that? Electric field at point A and point B are almost same. So if electric field is same, whenever you keep a charge in an electric field, there will be a force acting on it. So what is that force? The force acting on the charge is given by Q into E. Okay, so Q into E is the force that is acting on a charge kept in an electric field. So if you want to move this charge, you have to apply minimum this amount of force to move the charge. Okay, so when you are applying this amount of force, what is the work done to move it by a distance of delta L? Delta L is the distance between A and B. So the work done is given by F into X or F into delta L. Okay, or it will be Q into E into delta L. Now you are calculating work done. So work done, no matter how many methods you use, the work done in both methods should be same. So comparing equation 1 and equation 2, we can say that minus Q delta V must be equals to Q into E into delta L. Okay, these two work done must be equal. So Q gets cancelled and we get E equals to minus delta V by delta L. And in differential form, we can write this as dV by dl. Okay, this is the relationship between electric field and electric potential. Okay, now you have to remember that electric field is pointing from higher potential to lower potential. That is why there is a negative sign. The negative sign signifies electric field points in the direction of higher potential to lower potential. Okay. Now, derive the expression for electric potential at a point due to a point source charge. This is a 5-mark question and this is the most important derivation from this chapter. Okay, almost every year, I will not say every year, but almost every year this question has come in your board exam. Okay, so this is the star question of this chapter. So if a derivation is coming from this chapter, then 90% chance that this will be the question. There are 10% cases, there are some other questions have come, but out of the 3 papers, so if you are applying for improvement exam as well, out of the 3 papers, at least one of them will have this question. Maybe it is your first time paper, maybe it's your second time paper, maybe the third time paper, but this question will come every year. So in that sense, it has came every year. Okay, so first of all, you have to draw a diagram. We have to take a charge, say capital Q, and we are trying to find electric potential at some point R, at a distance R. So at a point P at a distance R from this source charge. Now for that, what you have to do, we have to remember the definition of electric potential. We have to go certain beyond and we have to add some dots as well. So this is say a point A, this is say a point B, and the distance between them is dx. Okay, they are very close points, close friends. Okay, now what is electrostatic potential? Electrostatic potential is defined as the work done to bring a unit positive test charge from infinity to a point in electrostatic field. Okay, so that means if you take a unit positive charge, okay, a test charge, unit positive test charge, and if you are bringing it from infinity to that point, okay, then whatever work that you are doing is basically the electrostatic potential at that point. Now infinity is a something which is we cannot easily handle. Right, infinity is something bigger than you can imagine. So that's why what we will do, we will imagine an intermediate point at a distance x. We will imagine an intermediate point at a distance x, A, and we will find if I am moving this charge from A to B, where A and B are very close to each other, then how much work I have to do. Okay, then we will extrapolate that from infinity till the point P. That is the process, because infinity is beyond us. Infinity, if we start at infinity, we will not be able to calculate, and that's why the mathematics is developed, the mathematics that is required for physics. If you know, Newton developed differentiation and integration, because physics required integration and differentiation particularly to handle such cases. Okay, so if you start at infinity, you will not be able to solve this problem. So for that you have to take some intermediate point, which is actually finite point, then we will extrapolate that. So how to do that? So first of all, we will assume that these 2 points are very close to each other, so that means electric field is constant at this point. Okay, electric field is constant at this point. Okay, so if you take a charge, say test charge Q, if you keep a test charge at Q, what will be the electric force that will be acting on this? So electric force acting on this charge is given by Q into E. So the force that is acting on this charge is Q into E. Now if you want to move this charge from A to B against the electric field, if you are moving it against the electric field, then you have to apply this much external force to move this charge. So what will be the external force that will be required? The external force that we have to apply must be equals to opposite to that of this force. Okay, this force is, suppose this is positive, this force is trying to take it away, so you have to apply external force which is against this internal force. This is internal force, the external force has to be opposite in direction, that's why minus Q into E, that is the force that you have to apply. Now if you are applying this much force and if you are moving it by a very small distance dx, then what the work that you are doing? The work that you are doing is given by the external force times the displacement. Force times displacement into cos theta. Here cos theta is 0, theta is 0, so cos theta is 1. So F external into dx, this is your work done. Now let's put the value of this Q into E dx. Okay, now this point is at a distance x, so we know from the concept of electric field at a distance x is given by K, this charge capital Q, divided by the distance square and dx. Okay, why? Because electric field is given by KQ by K capital Q by x square, right? Here we are assuming the charge, original charge is capital Q, that's why capital Q we have used here, right? Now what we have to do, we have to just calculate the total work done. Now for here, obviously K, capital Q, small q, they are constants, and what we have is dx upon x square. Okay, so this is the small work that you have done to bring the charge from very small distance B to A. But this is not our work. Our work is not yet done. We have to do more work because we have to start at infinity and we have to calculate the total work. So how to calculate the total work? For that we have to start at infinity and we have to reach our destination point at a distance r, and we have to integrate this entire thing minus K capital Q dx upon x square. Obviously this one is constant, so this one constant means this will straight away come out of the integration, right? Any constant comes out of integration and differentiation. K capital Q small q integration infinity to r. Okay, now what? Now this will be equals to minus K capital Q small q. Now what is the integration of 1 upon x square? Integration of 1 upon x square is minus 1 by x. So when you first started at the beginning, okay, when you just started at a PU2, chapter 1 was over, chapter 2 was over, and teacher was doing this derivation, you thought, what is this integration? Because you had no idea about integration back then. Okay, integration was not yet to be taught to you in your PU board. Most of you, some of the colleges, some students are smart, they already realized, but at that point of time it was very difficult for you to remember. You have to do the integration x to the power of minus 2 plus 1 minus 2 plus 1. Now you are familiar. Okay, 1 upon x square means it is be minus 1 by x. right? So as the time progresses, you are improving, so you have to improve with this as well. Okay, so minus and minus gets common and it become cancels each other. So K, capital Q, small q, and we put the value of this 1 upon r minus 1 by 1 upon infinity. Now 1 upon infinity is 0, x by 0 is infinity, something by infinity is 0. Okay, so we get this as K Q Q by R. Now whatever we have calculated is work done, and work done to move a test charge Q. What is electrostatic potential? Electrostatic potential is defined by work done to move a charge from infinity to a point by unit positive test charge. So unit positive test charge means here you have to divide this work done by small q. This is the test charge. Instead of taking 1, we have taken q. So finally we have to divide it by q. So we get this as K Q by R. Now K value is 1 by 4 pi epsilon naught. Finally when it time for the result, you put the exact value. So before going into a marriage, you dress up, right? You put your best shirt on, your best perfume on. So similarly at the this is the wedding dress. So for wedding dress you have to put up the 1 by 4 pi epsilon naught as a value. Okay, this is starting point 1, this is second stage 2, and this is the final concluding stage 3. Okay, now let's move on. Obtain an expression for potential energy of an electric dipole placed in an uniform electric field. So we have a uniform electric field, and a dipole is placed inside this electric field. We have to calculate the potential energy of this dipole. Okay, so when you place a dipole in an electric field, first of all you have to remember what is the torque acting on it. The torque that we have calculated was given by PE sin theta, right? PE sin theta. Now torque is equivalent to force in rotational motion. Okay, if you remember rotational motion, torque is equivalent to force in rotational motion. So when we calculate the potential energy, we calculated the work done. So potential energy is equals to work done. And what was work done? Work done was given by force into displacement, right? Force into displacement. Similarly, work done can also be calculated by torque into angular displacement. Torque into angular displacement can also be work done. That's what we are going to use in this case. So the potential energy is basically, first of all, obviously small potential energy. Small potential energy is equals to small work done, and that is given by torque into d theta is the work done, or PE sin theta d theta. Okay, so this is the way to calculate the total energy. So total energy must be equals to integration PE sin theta d theta. Again another integration that you are struggling with at the beginning. So it is PE integration. Now integration has to have some limit. In physics, whenever you are doing an integration, it has to be a definite integration. Now we have to when you are rotating the dipole from some angle and reaching at an angle theta, you are assuming that initially the potential energy at that particular location is 0. Okay, and then when you are rotating it, the whatever final position is, that is the final energy. Okay, so work done means you are moving it, you are rotating this dipole from some initial angle to some final angle. Now in case of potential, we assume that potential when it is rotated exactly like at an angle 90 degree, the potential is 0. Okay, and from there whatever angle it is gone, that is the final potential. So we will start at an angle of pi by 2 and we will reach our destination theta. Okay, so it will be, why we are taking pi by 2? Because we assume that potential energy is 0 at an angle 90 degrees. We will see that eventually. So from here we get P. What is the integration of sin theta? Integration of sin theta is minus cos theta, and it is pi by 2 to theta, or equals to Pe minus cos theta minus 0. Cos pi by 2 is 0, so we get this as minus Pe cos theta. Okay, now you can start it from 0 as well, does not matter, but this is the easiest way, because we know that potential energy when theta is 90 degree, potential energy is 0. So potential expression for potential energy is minus Pe cos theta, or it is minus P dot E. Both are vector, so finally you have to add the vector form as well. So this is the final result. Okay, remember these steps. This is slightly tricky because this is something which we do not do every day. Okay, electric field, electric force, still common, but from rotational motion to work, we generally do not calculate too many of cases. That's why this can be slightly tricky, but if you remember that you have to start from the torque, then you are good to go. Now this question, this is taken from one of your previous year papers. So this question is not a single 5-mark paper, a 5-mark question, but it is a 3+2 question. So 3-mark question was that one. Now this is the 2-mark question. Define energy density of a charged capacitor. How is the energy density related to the electric field present between the plates of the capacitor? So energy density is defined as, energy density is given by small u. It is defined as energy stored in the capacitor divided by the volume of the capacitor. This is called energy density. So energy stored in a capacitor per unit volume is called energy density of the capacitor, and it is denoted by small letter u. Small letter u is given by half epsilon naught E square. The derivation is now out of your syllabus, but this is the relationship between energy density and electric field. So energy density is directly proportional to the square of the electric field. Okay. Now next, another 2+3 question. What is the polar and non-polar molecules? So non-polar molecules are those which the center of positive and negative charges coincide normally. The molecules has no permanent or intrinsic dipole moment. So in this case, positive and negative, they coincide. Polar molecules are those in which the centers of positive and negative charges are separated even when there is no external electric field. Such molecules have permanent dipole moment. So in molecular level, a polar molecule has permanent dipole moment. Example you can add is water. Okay, here the example is carbon dioxide. Carbon dioxide is an example of non-polar molecule, and water is an example of polar molecule. Okay. Okay. Now next, derive the expression for the capacitance of a parallel plate capacitor. Again, important derivation. This can be coming as a 3-marker separate question. This can be coming as a part of a 5-marker question, but itself this question will not come as a 5-marker. Okay, this is a 3-marker question. Can be asked in a short answer type 3-marker. It can be asked in a derivation as well. So here we have a capacitor. Area of the capacitor say A. The distance between the plates say D. Okay, and you have applied a potential of V across the capacitor. Now the charge which is stored on this capacitor, say this is plus Q, this is minus Q. Okay, the potential that you have applied is V. Okay, now this can be considered as a very large charge sheet. So in case of charge sheet, we know that electric potential near the charge sheet is constant, and what is the electric field near a charge sheet? It is given by sigma by 2 epsilon naught. Electric field is given by sigma by epsilon 2 epsilon naught near a charge sheet. Okay, now electric field here, if you consider the zone number 1, we will get the electric field in zone number 1 is given by sigma by 2 epsilon naught. Due to this positive, should be away from, it will be away from. Similarly, electric field due to this negative will be towards. So sigma by 2 epsilon naught minus sigma by 2 epsilon naught, this is due to the positive charge, this is due to the negative charge, it will be 0. Similarly, if you consider this zone number 2, you will get the same result. So E2 and E1 will be equal, and outside the capacitor plates net electric field will be 0. But if you consider the zone number 3, then you will get something interesting. So in zone number 3, electric field due to the positive charge will be away from, and due to the negative charge will be towards. Okay, so positive and negative both will be in the same direction for zone number 3. For zone number 3, the electric positive and negative electric field both are in the same direction. So the net electric field will be sigma by 2 epsilon naught plus sigma by 2 epsilon naught, that is sigma upon epsilon naught. So this is the electric field in zone number 3. And the potential that you have applied is applied only in zone number 3. So we know that electric field is given by dV by dL, right, when small voltage difference is there. Here the voltage difference is given by V. So voltage difference is given by V, and the distance is given by D. The distance is given by D. So electric field can be written as V upon D. Okay, magnitude. Okay, so this must be the electric field in zone number 3. So we will use that as well. So V equals to E3 equals to V by D equals to sigma by epsilon naught. Now what is sigma? Sigma is charge density. Charge density means total charge on a plate divided by the surface area. Surface area is A, okay, and total charge divided by surface area is the charge density. So we will put that as well. So we get Q by A into epsilon naught. Okay, or Q equals to A epsilon naught upon D into V. So we just cross multiplied and we have organized it. Now for a capacitor, we know that Q is given by C into V. So this is our equation number 1, this is our equation number 2. So if you compare equation 1 and 2, you will see that Q is common, V is common, only thing that is not common is this, that means this must be equal. So C is given by A epsilon naught upon D. So this is the derivation of the capacitance between two parallel plate capacitor. Okay, easy derivation, not difficult. Practice 2-3 times, you will be able to remember it. Now next, calculate. Now we are time for us to solve some numerical questions. Calculate the potential at point P due to a charge of 400 nanocoulomb located 9 centimeter away. So calculate the potential at point P due to a point charge of 400 nanocoulomb located 9 centimeter away. So this is the location of the charge, this is the point, and the distance is 9 centimeter. 9 centimeter means 9 into 10 to the power of minus 2 meters. So whenever you see a centimeter, you always have to convert it into meters with this formula. Okay, always multiply with 10 to the power of minus 2, you will calculate. So first you have to calculate the potential. So what is the formula for potential? Formula for potential is, let me start from here. Okay, there is a part B as well. So let me start at here. So V equals to K Q upon R. Okay, so K is 9 into 10 to the power of 9. The charge is 400 nanocoulomb and the distance is 9 centimeter. Now cancel, 9 cancel, 10 to the power of 9, 10 to the power of minus 9 cancels. So you get 400 into 10 to the power of 2 or 4 into 10 to the power of 4 volt. This is the electrostatic potential. So potential we have calculated. Now what? Part B. Obtain the work done in moving a charge of 2 nanocoulomb from infinity to the point P. Okay, now we are trying to calculate to bring a charge from infinity to this point P. Okay, so work done is given by, work done to bring a charge from infinity to a point is given by magnitude of the charge times the potential at that point. Magnitude is given by 2 nanocoulomb, that means 2 into 10 to the power of minus 9, and voltage is given by 4 into 10 to the power of 4. So that will be 8 into 10 to the power of minus 5 joules. Okay, or this can also be written as 80 microjoules. Okay, 10 to the power minus 6, 10 microjoules. So 80 microjoules can also be answered. Now the part says that does it depend on the path along which the charge is taken. So if you see the calculation, the path is not involved. Also you should know that electrostatic field is a conservative field, so it is independent of path. No, answer for the second part you have to mention a no, it does not depend on the path taken. This is very, very important. If you miss that, 1 mark will be lost. Okay, for just writing this statement you will get 1 mark. Okay, so correct answer is 4 into 10 to the power of 4 volt, 8 into 10 to the power of minus 5 joules, and last part no. So everything you have to answer, otherwise you might lose marks. So be careful. 3 capacitors of capacitances 2 microfarad, 3 microfarad, 6 microfarad are connected in series. Determine the effective capacitance of the combination. So here we have a 2 microfarad, a 3 microfarad and a 6 microfarad are connected in series with some battery. Battery initially is not required. 2, 3 and 6, all of them are microfarad. Now first stage is to calculate the effective capacitance. So how to calculate effective capacitance? 3 capacitor connected in series. So equivalent capacitance will be 1 by C1 plus 1 by C2 plus 1 by C3. Okay, not 2. In case of 2, you know the shortcut C1 C2 by C1 plus C2. But here we have 3, so we cannot use that shortcut. So 1 by 2 plus 1 by 3 plus 1 by 6. So if you see that microfarads 10 to the power of minus 6 factor we have not used here. Why? Because that is common and our result will also be in microfarad. So now the resultant of them is 6. So 3 plus 2 plus 1. So 3 plus 2 5, 5 plus 1 is 6. So 6 by 6. So it is equals to 1. So C equivalent must be equals to 1 microfarad. So first part is 1 microfarad, done and dusted. Next, find the potential difference across 6 microfarad capacitor if the combination is connected to a 60 volt supply. Okay, so we have to calculate the potential difference across this one. If a 60 volt supply is connected. Okay, so for that we will use this C equivalent and we will find what is the charge that is flowing in this circuit. Okay, charge in a series combination remains constant. So if we replace this circuit using a equivalent capacitance circuit, the charge should be same. Okay, charge should be same. Now what is that charge? So Q should be equals to C equivalent into the voltage that you have applied, and Q is given by 1 microfarad, that is 1 into 10 to the power of minus 6, and voltage is 60. So this is the charge that is flowing through each of the capacitor. Now if the voltage across this 6 microfarad is V, then what is the charge of this capacitor? Charge of this capacitor will again be Q, because it is series combination, and that is given by 6 microfarad into the potential across this. Now this is equation number 1, this is equation number 2. So if we compare these two equations, we get 1 into 10 to the power of minus 6 into 60 equals to 6 into 10 to the power of minus 6 into V. Okay, so first thing, calculate the charge. First step is to calculate the charge. Okay, then calculate the charge for equivalent as well as calculate the charge for this. Both charges should be same. Okay, and you just need to compare these two values. One of them will have this unknown V, and then you can easily calculate V. 10 to the power of minus 6 cancels, so V must be equals to 60 by 6, that is equals to 10 volt. Okay, if you have any doubts regarding this numerical, you can mention that in the comment section below. This is easy numerical, just follow the steps and you will get the full marks. Okay, 1 microfarad, 10 volt. In a parallel plate capacitor with air between the plates, each plate has area of 4 centimeter square and the distance between the plates is 2 millimeter. Calculate the capacitance of the capacitor. Take epsilon naught equals to 8.854 into 10 to the power of minus 12. Now you will use this. I personally will use 9. So when you are writing this in an exam, the value of epsilon naught will be given to you. You have to use that, and you have a small simple calculator, so you can calculate it. I do not have calculator, so I will use 9. Okay, so that is my benefit, but when you are solving in the exam, because you have access to a simple calculator, use the exact value. Okay, if this capacitor is connected to 100 volt supply, what is the charge on each plate of the capacitor? So first we will calculate the capacitance, part A. So what is the formula for capacitor? Formula for capacitor is simple A epsilon naught by D. Yes, the same formula that we derived few minutes back. Okay, so here area is given by 4 centimeter square. So 4 centimeter means 4 into 10 to the power of minus 4 meter square. Okay, 1 centimeter is equals to 10 to the power of minus 2 meter. So 1 centimeter square means 10 to the power of minus 2 whole square meter square. So basically you are taking square on both sides. 1 square does not change anything, so that is equals to 10 to the power of minus 4 meter square. So these conversions, if you remember, it will be very handy. So area is 10 to the power of minus 4, 4 into 10 to the minus 4. Epsilon naught, as I mentioned, I will take 9. Sorry for that. Okay, answer will differ by a small margin. The distance between the plates is given by 2 millimeter. 2 millimeter means 2 into 10 to the power of minus 3. Okay, 2 into 10 to the power of minus 3 is millimeter. So 2 is 4. So 2 into 9 is 18 into 10 to the power of minus 13, or 1.8 into 10 to the power of minus 12, or 1.8 picofarad. Okay, 1.8 picofarad is the capacitance. Easy. Now next part number B. If this capacitor is connected to a 100 volt supply, what is the charge on each plate of the capacitor? Charge on each plate of the capacitor is given by Q is equal to C into V. C we have calculated this. So 1.8 into 10 to the power of minus 12. Voltage is given by 100. So it will turn out to be 1.8 into 10 to the power of minus 10, or 0.18 into 10 to the power of minus 9 or 0.18 nano coulomb. This is coulomb, everything is coulomb. Okay, so final answer is 0.18 nano coulomb. Easy question, nothing, no rocket science. Apply the formulas, calculate by step, and you will get the answer. So 1.8 picofarad and 0.18 nano coulomb. Okay, now I think this is the last question so far. This question is from your model question paper. This is also from your model question paper. 3-point charges 3 nanocoulomb, minus 2 nanocoulomb, 4 nanocoulomb are placed at the vertices of A, B and C of an equilateral triangle ABC of sides 0.2 meter. Calculate the potential energy of the system. Also calculate the amount of work required to place the same charges at vertices of an equilateral triangle of side 0.1 meter. So let's see. So here we have 3 charges on the vertices of an equilateral triangle A, B, C. So what is the distance between the sides? Distance between the side is 0.2 meter. Each side is 0.2 meter. Now charges are placed at A 3, B minus 2 and C 4. So this is the system of 3 charges. Now we know that the potential energy between 2 charges K, Q1, Q2 by R. What about 3 charges? So potential energy of 3 charges is slightly tricky but not super tricky as well. So it is given by K, Q1, Q2 by distance between them plus Q2, Q3 divided by distance between them plus Q3, Q4, Q3, sorry, not Q4, Q3, Q1 divided by distance between them. Okay, so this is the potential energy of 3 charges. Right, now potential energy of 3 charges is given here. Now if you see this, all cases the distance is same. This is R, this is R, this is also R. All 3 distances are same. So we know that for this particular problem R12 equals to R13 equals to R31 equals to R. So this 1 upon R from each equation will be common. So therefore we can write the potential energy of the system is given by K upon R Q1 Q2 plus Q2 Q3 plus Q3 Q1. Okay, so we will calculate these things one by one. So K by R, I am writing K by R. I will try to calculate this one first. Okay, we will try to calculate this one first. What is the first charge? Q1. Q1 is 3. What is the second charge? Second charge is minus 2 plus minus 2. What is the third charge? Third charge is 4. And first and third charge 4 into 3. Now we will put the value. K by Q minus 6 minus 8 plus 12. So it will be minus 14 plus 12, that is K by Q, sorry, K by Q, no, K by R. So it will be minus 2. So now we will calculate the potential energy. U equals to 9 into 10 to the power of 9, that is the value of K, and distance is 0.2 into 10 to the power of and one more thing, they were all nanocoulombs. So nanocoulomb means nanocoulomb, 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 nanocoulomb. That means here we also have to multiply with the factor of 10 to the power of minus 18. That one we have not done over here. So that also there, because nanocoulomb square is there. Okay, so two charges are getting multiplied, that means nanocoulomb's square is there, so that's why this is turning out to be minus 2 10 to the power of minus 18. So minus 2 10 to the power of minus 18 and minus 2. Okay, so this will turn out to be 1 0, 2 cancels and 1 0 goes up, so 9 into 10 to the power of minus 8. So 9 into 10 to the power of minus 8 is the potential energy, that is joules or 90 nanojoules. Okay, 90 nanojoules. Nanojoules is the potential energy which is of the system, of this system. Now second case, everything remains same. Okay, this is the first case. In the second case, what we have done, this is answer A. In the second case, what we have done, we have from this system we have moved it to another triangle of distance 0.1 meter. Okay, so first we will calculate at this combination what is the potential energy of the system. So this one will become our initial potential energy and this one will become our final potential energy. So we will calculate the final potential energy. What is the formula for final potential energy? Everything is same. Okay, only the distance will be changed. So K by R dash Q1 Q2 plus Q2 Q3 plus Q3 Q1. Okay, now that's why I have done this calculation like this, so that you can write the answer in one line. Okay, this is why you have to be careful, same formulas is being used once or twice. So K value is 9 into 10 to the power of 9, R value is 0.1 meter mentioned in the question. Okay, 0.1 meter, and this one we have already calculated, so we will not calculate once more. So minus 2 into 10 to the power of minus 18. So now simplify, you will get this exactly as 18 into 10 to the power of minus 8 or 180 nanojoules. So 180 nanojoules is the final potential energy of the system. So how much work you have done? The work that you have done is final potential energy minus initial potential energy, that is equals to 180 minus 90 equals to 90 nanojoules. So same formula we are using two times. First we are calculating for the bigger configuration, second time we are calculating for the smaller configuration, and they said what is the work done to take the same charges to the new configuration, that will be final minus initial. And one more thing I missed, there is one thing I missed, is that this will be a negative sign. There will be a negative sign. This negative sign I have missed. This negative sign was here. Similarly here as well there will be a negative sign, and this final result will also be negative. Okay, final minus initial, both of them are negative, minus 180 and minus 90. Okay, so you might be thinking, sir, there is a negative sign you missed. Yes, I missed it, so now I have added it. Okay, so negative 180 minus negative 90, that is plus 90, so that will become minus 90 nanojoules. Okay, so this is the question from your model question paper. So practice this question, maybe similar question will come. So this is slightly trickier than previous year questions and from previous year model papers, but again not super difficult. Only the thing that you need to know one formula, you have to apply the same formula two times to solve this question. Okay, so I hope you enjoyed today's session. Also, if you have not yet subscribed to our channel, please don't forget to subscribe to our channel. I'll be back with current electricity in our next Brahmastra series. Till then, bye.